Assalamualaikum and good morning to our panels. We are from EH2208D. We will be presenting about production of 41,000 metric ton of isopropanol per year. My name is Muhammad Zafkan bin Zabi.
My name is Muhammad Adi bin Aziz.
My name is Nur Atika binti Kamar Zaman.
My name is Nur Izzati binti Muhammad Arifin.
My name is Nurofana binti Muhammad Zaidi.
And I'm Nurul Maisara binti Khalid.
Okay, now let's start with the presentation.
Before moving on to the main topic in the presentation, I, Nurofana binti Muhammad Zaidi, would like to give a brief introduction in order to provide a better understanding on the process background and site location. Our plant manufactures 41,000 metric tons per year of isopropanol through a direct hydration process. It is a process of producing isopropanol from propylene and water as a raw material via a single-step reaction. There is also a byproduct produced in the process, which is diisopropyl ether. The presence of amylase catalase is to ensure a high selectivity towards isopropanol with a high purity of 96%. As for the location of the plant, it will be constructed in Kerteh Industrial Area Terengganu, as this site is strategic in terms of raw material availability, excellent readily available infrastructures, and introduction towards internal and external investors.
Hi, Assalamualaikum. I am Nur Izzati and today I'm going to present about the process integration of our plant. The table shown is the list of heat exchangers and streams involved in the pinch analysis with their respective supply and target temperatures. There are 10 heat exchangers involved and the minimum temperature difference for this pinch analysis is 10 degrees Celsius. The method used for the pinch analysis in this design project is problem target analysis (PTE). The main objective is to improve energy efficiency and to reduce the operational costs. The red arrows shown in the figure indicate the temperature changes for hot streams, while the blue ones indicate the temperature changes for cold streams. Based on the PTE, the pinch temperature obtained is 45 degrees Celsius. The minimum heat required for hot utilities is 2,166 kW, meanwhile, the minimum heat required for cold utilities is 375 kW. Proceeding to the heat exchanger network HEN, the pinch temperature obtained from the PTA was used. As stated previously, the temperature difference between two sharing streams should not be lower than 10 degrees Celsius. Based on the HEN illustrated, it can be seen that there are 7 new heat exchangers, 4 heaters and 2 coolers needed for the production plant. Lastly, the comparison between before and after integration was done in the process integration. Despite the fact that the number of equipment needed for the plant increases, however, the percentage of utilities saved after integration is also significant. Therefore, we proceed with the heat integration to improve energy efficiency and, most importantly, to reduce operational costs. With the heat integration being applied to our production plant, the new process flow diagram is as shown in the slide.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adi bin Aziz and now we proceed to chapter 8, which is process control. Now we look at the control device installed in our reactor R101. The first objective strategy is to achieve the desired temperature of the outlet product stream by controlling the flow of cooling water. The control strategy we use is installing cascade control. Transmitter will detect the deviation of temperature and flow controller. It will send the signal to the control valve to open the valve to allow the cooling water. The control variable for this objective is temperature inside the reactor. The manipulated variable is the inlet flow of cooling water, and our set point is to maintain the temperature inside the reactor, which is 250 degrees Celsius. The next objective is to maintain the inlet flow. For this objective, our control strategy is installing feedback controller. The control variable of these objectives is the feed flow rate to the reactor, and the manipulated variable is the feed flow rate. Our set point is to maintain the inlet flow rate 2600 kg per hour. And the last objective strategy is to maintain the pressure in the tank. We use cascade control as our control strategy for this objective. The control variable is pressure inside the tank, the manipulated variable is flow rate of outlet stream, and our set point is the pressure relief valve will open when the pressure above the set point, which is 8990 kPa. We proceed to heat exchanger E101. The objective strategy is to control the optimal temperature. We install feedback controller as our control strategy. The control variable is the product outlet's temperature, the manipulated variable is the cooling water flow into heat exchanger, and our set point is low temperature at 46.99 degrees Celsius. Here is overall control device installed in our process plant. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Maisara binti Khalid and I would like to present about the equipment design for fixed bed reactor R101. In this process, solid catalyst was used. So, our group decided to choose fixed bed reactor as the type of reactor for our production because it is much more suitable compared to the other type of reactor. The main purpose of this reactor is to convert the raw material, which are propylene and water, at the temperature of 134 degrees C and the pressure 8,919 kilopascal into a product known as isopropanol. There are few assumptions that have been made throughout the design, which are the reaction occur in the reversible reaction and the conditions of the reactor is non-isothermal. The main objective of this reactor is to achieve a required conversion. And according to the ONU 1973, the required conversion for this reactor is 80%. Now I'll proceed with the chemical design. So here is the summary table for the chemical design. Based on the calculation, the volume of the reactor is 2.75 meter cube and the length of the reactor is 5.24 meter. As for the diameter of the reactor, the value obtained is 1.05 meter squared. For the cooling system, the type of coolant used is cooling water. And for the tube arrangement, the tube arrangement is in a square pattern and the number of tube is 171 and the number of buffer is 9. The function of buffer is to prevent the backflow. Now, I'll proceed with the mechanical design. Mechanical design is more focused on the design styles of the reactor. So, here is the summary table for the mechanical design. The material of the construction that we use is stainless steel 304, and for the vessel specification, the minimum wall thickness is 43.76 mm, and the type of dome that we use is ellipsoidal. The thickness of the dome is 42.16 mm. So, here is the engineering drawing for the fixed bed reactor R101.
For this section, I will explain the equipment design involved for the separator vessel unit, which is V101. The purpose of this unit is to separate the liquid and vapor mixture of the product from the reactor, which consists of propylene, propane, water, isopropanol and diisopropyl ether, as shown in the figure. The vapor product will be treated while the liquid product from the vessel will proceed to the light gas tower. After the calculation have been made, it is discovered that the desired diameter and height of the vessel will be 1800 mm and 9000 mm respectively. The volume of the vessel will be around 22.9 meter cube. As for the material of construction for this unit, the vessel is made from stainless steel 304, whereas the skirt support with a height of 2700 mm is made using carbon steel. Stainless steel is chosen as a vessel material of construction due to the properties of component, which is diisopropyl ether. It has a slight corrosive properties which can damage the internal linings of the vessel. For the design pressure and temperature, 10% above the operating pressure and temperature is taken for safety consideration. Hence, the design pressure for this vessel is 1.21 bar and the design temperature is 303 Kelvin. The separator column will be oriented vertically with an ellipsoidal head with a height of 420 mm and has an insulation that made up from mineral wool. The figure shows the summarized AutoCAD drawing for separator vessel V101, which consists of sectional of top and side view of the vessel, as well as additional dimensions for the mister pad.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adi bin Aziz and now we proceed to heat exchanger design E102. The purpose of heat exchanger E102 is to increase the temperature of fluid stream from 30.05 degrees Celsius to 50 degrees Celsius before it entering reactor R101. The assumption made for our chemical design is there is no heat loss to surrounding, the surrounding temperature is neglected, and lastly the kinetic and potential energy change are neglected. For our heat exchanger design, we use shell and tube heat exchanger. This is because it can sustain a wide range of process conditions including temperature and pressure. Heat loss Q is 215.84 kW. Heat transfer area is 6.77 meter cube and the overall heat transfer coefficient is 246.04 watt per meter cube degree Celsius. In our mechanical design, we use ellipsoidal for our heat enclosure. We also use welding neck flange for our flange with 17 number of baffle. For our shell and tube material construction, we choose to use carbon steel. For chemical design, on the shell side, we use 4 shell passes with pressure drop 100.2 Pascal with triangular arrangement. In our tube side, we use fixed tube as our type of tube with 2 passes and 2.43 meter of tube length. The pressure drop for our tube side is 58.2 Pascal. Here is my design drawing for heat exchanger E102. That's all from me, thank you.
The purpose of light gas tower is to separate unreacted propylene and propane. For the operating conditions, the feed is fed into the columns at 50 degrees Celsius and 9.678 atm. The product at the top streams will leave at 53.19 degrees Celsius and 1 atm, while the product at the bottom stream will leave at 84.39 degrees Celsius and 1.184 atm respectively. The light key component is diisopropyl ether since it is more volatile component, while the heavy key component is water and it will be removed at the bottom stream since it is relatively less volatile component. From the summary tables, the diameter of the columns is 1.59 meters with a height of 40 meters. The chosen materials of constructions is carbon steel since it is widely used in the industry, and the selection need to take into consideration the compatibility of the materials with the working environment. The number of stages is 20 stages including reboilers, and the feed point locations is at stage 15 from the bottom. The type of supports chosen is the straight cylindrical supports with the chosen material of constructions is carbon steel. This is the AutoCAD drawings for the light gas tower with the design specifications from the summary table.
The next one is the design of heat exchanger E107. The function of this heat exchanger is to cool down the process fluid temperature coming from the light gas tower from 84.45 degrees Celsius to 40 degrees Celsius. It is a fixed tube, shell and tube heat exchanger with 2 shells and 4 tube passes. The cooling medium used in this heat exchanger is brine solution. The reason for this choice is because it is a comparatively low-cost material with great heat transfer efficiency. For the fluid allocation, the process fluid flows into the shell side while the brine flows into the tube side of the heat exchanger. The heat duty for this heat exchanger is 380 kW. Meanwhile, the overall heat transfer coefficient is 123 watt per millisquare degree Celsius. From the design calculation, the AutoCAD drawing is as shown in the slide. After considering the chemical and mechanical design calculation, the number of tubes obtained is 438 with 110 tubes per pass. The diameter of the shell calculated is 624 mm. The length is 4880 mm, whilst the outer and inner diameters of the tubes are 20 and 16 mm respectively. In this design, the corrosion allowance being taken into consideration is 2 mm. The most suitable type of head for the heat exchanger is ellipsoidal head. The baffle spacing for the single segmental baffle in this design is 310 mm. For the material of construction, carbon steel is used to construct the both shell and tube sides of the heat exchanger since it is relatively cheap and widely available. It also has good tensile strength and ductility.
Assalamualaikum and a very good morning. I am Muhammad Zafkan bin Zabi and will introduce you to the DMSO water column design, which is a very crucial in this production of isopropanol as it recycles down the solvent used in the extraction column to obtain a better purity of the final product. The key component in this column, which consists of light and heavy key, are water and DMSO respectively. Based on the calculation, the number of trays needed are 11 trays, including reboiler, with spacing of 0.6 meter. The column efficiency is expected to be 43.65%. The plate thickness is set to be 3 mm each. The carbon steel material is chosen after selection are made based on the scoring method. The type of insulation is mineral wool with the thickness of 60 mm. Torus spherical head is chosen with the thickness of 0.3172 mm. The conical support is selected, which made from carbon steel as well, and the same material is also used for the design of the nozzle. As you can see in this slide, this is the design of T103 Demeso water column design, which consists of multiple views with each scale respectively.
Next is Chapter 10, Economy Analysis. The profitability analysis is estimated using CapCost software. These are the values that will be used in the profitability analysis. The plan starts up at the end of year 3 and the construction period is in 3 years. The taxation rate is at 24% and the project lifespan is estimated to last 20 years. From the non-discounted graph, the payback period is 3 years with the rate of return on investment, also known as ROI, is at 34.03% per annum, where the benchmark of ROI for the project to become profitable need to be more than 10% per annum. From the cumulative cash positions, the value is in positive values, which is Ringgit Malaysia 54.66 million, which shows that the project will gain more profit at the end of the project lifespan. From the discounted graph, the discounted payback period is at 3.62 years, with the value of PVR is at 1.63, which shows that the project is profitable since the value of PVR is more than 1. At the end of the project lifespan, the NPV that the plan will get is at Ringgit Malaysia 20.27 million. In conclusion, both non-discounted and discounted cash flow diagram shows a positive trend over 20 years. Therefore, productions of 41,000 metric tons of isopropanol per year is a profitable project.
Now, I'll proceed with the chapter 11, which is plant safety and layout, and I will talk about high-rec. Identifying a possible hazard in our plant is one of the most important things that we have to do. Hence, few possible hazards in our plant was identified, but I will only talk about 2 possible hazards which are contribute to the high risk. The first one is during the transportations of the chemical. The hazard that had been identified is the chemical spillage, and also the worker may be exposed to the chemical toxicant while doing this job. The effect from this hazard is it may affect their respiratory system and can cause suffocation. In order to prevent this from happen, the control measure has been taken, such as the worker need to make sure that there is no leakage on the storage tank that has been used to store the chemical while transporting, and they have to wear a proper PPE while handling this job. The second point is during the maintenance work. The hazard that had been identified is noise pollution and falling from a high place. The effect from this hazard is it can cause injury and can cause hearing problem. In order to prevent this from happen, a safety briefing must be done before the worker proceed with their work, and the worker need to be provided with a proper PPE such as the earplug in order to prevent this unwanted accident.
Moving on to HAZOP. HAZOP is a technique for identifying possible hazard in a system and identifying operability issues that are likely to result in non-conforming products. The table shows the example of HAZOP for process vessels. Okay, let's see on the level parameters in the separator vessels. A low level in the process vessel normally is due to the blockage at the inlet stream, blockage at the inlet pipe, and also a cavity built up in the valve, which could lead to a no separation occurs and ultimately hindering the separation of the desired product. Therefore, The possible action that may be implemented to avoid this is by installing a level indicator and conducting a routine inspection in order to ensure it is constantly in a good condition. It also includes a regular monitoring of the process in order to identify any slight variation of the process variable that may be occurring. Another possible incident that could occur related to V101 is when the liquid level is too high. The cause of this could be either the high amount of liquid inlet compared to the outlet stream and possibly caused by the blockage at the outlet pipe. This could lead to inadequate product formation due to the flooding in the vessel and ultimately results in vessel rupture or explosion. The action required to avoid this is by installing a safeguard such as pressure and high liquid level indicator as well as regular performance monitoring on the unit. Another possible incident that could occur related to V101 is when the liquid level is too high. The cause of this could be either the high amount of liquid inlet compared to the outlet stream and possibly caused by the blockage at the outlet pipe. This could lead to inadequate product formation due to the flooding in the vessel and ultimately results in vessel rupture or explosion. The action required to avoid this is by installing a safeguard such as pressure and high liquid level indicator as well as regular performance monitoring on the unit.
The plan layout for this production may not only consist of major equipment process flow diagram, but also including to non-related to PFD such as administration area, storage area and gathering area. The plant area zoning is very crucial in determining the distance between hazardous area and also a safe area in the plant. The zone and area will be explained further in the next slide. The hazardous area is identified after HAZOP has been done for each equipment to determine the safe area around it. Hazardous Area Classification (HAC) standard give the industry accepted separation, distance between ignition source and credible source of flammable release. Primarily, the safe area in the plant is away from the zoning as you can see in the second picture. After hazardous area have been identified, the emergency escape route is proposed in the third picture as well. The zoning area are categorized into Zone 0, Zone 1 and Zone 2. Zone 0 an area in which an explosive atmosphere is present continuously for a long period of time or will frequently occur. Zone 1 an area in which an explosive atmosphere is likely to occur occasionally in normal operation. Zone 2 a place in which an explosive atmosphere is not likely to occur in normal operation, but if it does occur, it will persist only for a short period of time. Let's take a look at propylene, water and isopropanol tank as an example. These tanks are classified into Zone 2 as the section of the hazardous environment where flammable atmosphere is unlikely to exist under standard operating condition. These tanks also possess secondary grade release where a release that is unlikely to occur in daily operation. The fluid inside the tank are fluid category C. Those tanks contain flammable fluid are at temperature above their flash point when on release. A typical radius for this equipment is 3 meters away as a safe zone. These standards are based on the IP15 standard. Let's take a look at the conceptual design of the isopropanol production plant. It consists of major equipment, buildings and piping. You can see the office, laboratory and utilities room as well as gathering and loading area. And then this is the propylene and water tank as our raw material, followed with reactor, separator and combustion chamber. The mainstream will undergo a series of separation process in 3 different distillation towers. The distillate of the first tower will undergo into the flare tower at the corner of the plant area, while the bottom product will enter the second column where isopropanol product will exit at the top and store in the tank. Lastly, the distillate of the third tower will undergo wastewater treatment. The yellow pathway on the production plant represents the emergency escape route as proposed earlier. Thank you for watching.